Okay, welcome everyone. My name is Casey Wang, and I'm a co-PI on the Fabric project. Thank you all for joining us today for the 14th installment in our Stitching Together Innovation with Fabric Users webinar series. Today it will be led by Kong Wang, Ganesh Chanimalai Sankaran, and Ivan Torres. Now, next slide. Are we sharing the slide? Before we begin, I would like to first share a few housekeeping items. The webinar will have a live Q&A question and answer session following the presentation. Please note that the chat feature in Zoom has been disabled. For asking a question, you will type it into the Q&A box at the bottom of your Zoom screen, and we will answer it during the Q&A session. Finally, this webinar is being recorded, and it will be shared with all the registrants. Today, we are joined by our presenters, Kong Wang, Ganesh Chandamalai Sankaran, and Ivan Torres. So we'll probably need to go back a couple of slides. First, we'll introduce Kong Wang. Kong Wang is a senior researcher at RENCI at UNC Chapel Hill. He received his PhD from University of Massachusetts Amherst. Kong Wang has co-authored more than 40 papers with focus on networking, cloud, and distributed systems, and AI machine learning for infrastructure. Then we have Ganesh Chenmalai Sankaran. Ganesh has his bachelor's in electronics and communication engineering and higher degrees in computer science engineering. Ganesh has 2 decades of industry experience working for HCL Cisco and then for Dell Networking. Ganesh's expertise spans network management, network security, and network operating systems. Ganesh has been a part of 3 startups that have developed mobile application, SD-WAN, and optical computing hardware. Ganesh has co-authored 30 research articles and has been the primary contributor for 25 patents, including pioneering contributions to change detection and drop accounting, programming network switches, computing at high data rates, and designing converged hardware for computing and communications. These are Ganesh's recent interests. Ivan Torres is the third speaker. Ivan is a computer science graduate student at the University of Illinois, Chicago. His interests include distributed systems, networking, and high-performance computing. As an early career researcher, he has worked on projects exploring HPC infrastructure and network throughput experiments. Next slide, please. And now I will pass this to Kong to begin the presentation.
Thank you, Casey. Hi, everyone. So I'm Kong, and I'm going to be the first speaker here. Here's a brief outline that I will talk about throughout the talk. So first, we will introduce like some fundamental knowledge about P4 switches, as well as we'll compare the software P4 switches with the hardware P4 switches. And then we'll talk about the hardware switch, which is called a Tofino on Fabric. Next, we will talk about the how we port the software switch, the programmable P4 software onto the Tofino hardware switches. Next, we'll talk about the Fabric high throughput experiment we'll be doing for this webinar. And finally, Ivan will give a demonstration of the experiments we were running. So next slide, please. So first, I would like to briefly introduce you to 2 types of P4 switches. The first type is called a BMV2, which is the short term for the behavioral model V2. So it's a kind of a software switch it's mostly giving you the access to the reference implementation of P4, but you don't have to have the like the ASIC hardware, expensive hardware switch. It runs on CPU, and it supports sequential and soft pipeline. It's very flexible, but it's going to be much slower comparing to the hardware switches. And also, it's virtually unbounded tables and memories, and of course, it's limited by the host, but it's much easier to modify, so it's easier for people who started programming on P4. So overall, it's great for learning and debugging. And next is the Tofino switch, which is a programmable hardware switch ASIC introduced by Intel and Barefoot. It provides flexible. It provides the fixed stages. So in that case, you have to go through each of the stage. But however, with this with programmable hardware, it's able to provide the line rate processing with a much higher processing speed. And also it has the fixed pipeline depth. It's required to program on the hardware switches. And finally, this type of hardware switch is capable, and it's more suitable for production data plane high-speed networks. Next slide, please. So today we'll be talking about, we'll be focusing our experiments on the Tofino hardware switches. So basically, it's a programmable switch ASIC, and it provides a high throughput support. It can provide up to 66.4 terabits per second, which has up to 32 100 gigabits per second Ethernet duplex. And its architecture is it provides the multi-pipeline shared buffer, and it has 496 bus width, and with a unified buffer of 22 megabytes. And also it has the 25 gigabits of serializer and deserializer. On the right hand side, you can see the general pipeline for the Tofino switches. So it has a serializer and a deserializer, which will convert the high-speed serial bit streams from the physical link into the parallel data that the switch can process. And next, it goes to the packet buffers, which will temporarily store the incoming packets to absorb the bursts and can handle the contention. We highlighted the third stage as orange because it's mostly the programming will be happening over here. It's the core of the switch where the packets are parsed, and it can match to some specific rules and can be modified using the specific P4 defined the pipelines. Finally, it will go back to the serializer and deserializer again, which will convert the processed packets from the internal parallel format back to the high-speed serialized signals for transmission over the network channel. So next slide, please. So for the orange part, the programmable packet processing pipeline, it contains some fixed stages. If you want to process, if you want to really program your data processing pipeline, so it has the 6 sort of symmetrical stages. So the ingress parser will parse the raw incoming packet bytes into the structured headers, such as like the Ethernet or IP, and it will follow a state machine to identify the protocol layers and extract the fields for you to process. The next stage will be the ingress match action unit. So in this case, it will be able to perform the table lookup on the parsed header fields. and then based on the matches, it will be able to execute the actions such as to modify the headers, to update the metadata, or to select the output ports for some specific forwarding rules. And the third stage is the ingress deparser, so which will reconstruct the packets from the modified headers after we have done the ingress processing. So it will then serialize the header back to the byte stream in the correct order so that it can be then go back. It can then go back to the network for like further forwarding cases. And the fourth one will be the egress passer, which will reparse the packets after the buffering and the scheduling. Basically, it's about to be going out of the switch. In this case, especially if the metadata or the headers were changed in the egress, we'll be able to like do some further processing for the data right before the data leave us. And then after the parser, the egress parser, we'll then have our final egress match action unit. We'll be able to apply the like egress specific policies, such as like the queuing decisions or the traffic shaping or replication, things like that. Or like if we want to have like a final header updates, it will be able to wrap up the packet processing, and then it can use the metadata like the queue depth or timestamps for parsing for the matching and the processing. And the final stage will be the egress deparser. In this case, we just finalize the programmable packet processing stage, and we serialize the data so that it is fully capable to go back to the network pipe for the to continue be transmitted over the network. So next slide, please. Some further notes about the Tofino pipeline architecture. So on the left-hand side, we have the CPU pipeline, which is generally be used by the software switches such as the BMV2. And on the right-hand side, we have the Tofino pipelines. So as we see, like these are the more detailed comparison. So the CPU based pipeline is able to execute different instructions dynamically, like at runtimes, and such as like it can have branches or even loops. The control flow is relatively flexible and can change per packet. So that's why the BMV2 can support like a complex logic. And also it provides us the mutable data stream for which the memory can be read or written freely with like pointers or dynamic like or the dynamic structures or like the variable access patterns, and the packets can trigger like arbitrary memory operations. And the third one is the speculative execution. So in this case, the CPU will be able to predict the branches and execute ahead to improve the performance. However, this will like require the data processing, and if the data is not in the cache, maybe in the memory, the CPU will like wait for the data to be fetched from the memory. So in this case, this will introduce some variable delays, but it enables some more general purpose computation. So for the Tofino switch on the right-hand side, the pipeline is more like pre-compiled into fixed stages with the predefined operations. You cannot change the control flow at runtime, and also like each packet will carry its own header and like the metadata that are modified as the flows through the pipeline. So this does not have the like does not give us the flexibility of loops or specific like CPU-based instructions, because we have like fixed handling. So in this case, no loops and no flexibility. Once you compile it, it will stay there. So that's kind of the like the case for high throughput processing. This will provide us less flexibility, however, much better performance comparing to the CPU based the pipelines. So next slide, please. Yeah, so the on Fabric we provide the users like 5 Tofino switches. So these switches provide us the custom packet handling and forwarding and line rate communication between the ports, as well as each of the switches will support 4x4 node communication at line rate, and also provides us the distributed data plane with great flexibility. So next slide, please. So we will briefly talk about how you find the P4 resources on Fabric. So as we see, we have at the landing page of Fabric, we have this Tofino, we have this Fabric topology, and on each node, we should be able to find on the right-hand side, we should see a list of resources that are available from this site. So at the very bottom, you see like the switch part. For now, it has a 0/1. That means this side has in total one switch, one P4 switch, but the P4 switch is unavailable at this moment. So next slide, please. If you want to see more about each site's resources, you can click the site name. For example, here we are looking at this. We are looking at Salt Lake City. On the right-hand side, you see the Salt Lake City. It is clickable. So once you click that site name, you will be able to see a list of sites on Fabric. So here we see that like this is a screenshot of the list of sites that has many pages, and you can figure out which site has which resources. Because P4 switches are kind of rare at Fabric, is not showing up on this list of resources. So next slide, please. Then if you click on that specific site, you will be able to see a list of a detailed list of resources. So you can what you can look for is the site name dash P4 dash SW. That means the P4 switches contained by this site. So this button on the left side, that little plus is a clickable button. So once you click that button, you will be able to expand this into this view. So you see a table of the like resources like the core, disk, RAM, and the components for this specific resource. So that's how we, in general, how we look for resources from Fabric. So next slide, please. Yeah, then I'll pass on to Ganesh. So he will talk more about how we port the code from the software switches to the hardware switches.
Thanks, John. John briefly covered this. BMV2 is one of the platforms which is a software switch platform, whereas Tofino and there are other platforms that are more hardware oriented, and a software-based BMV2 is more like more conducive for initially starting up with P4. But then if we want to deploy it on a production network at like 100 gigabits per second, or like processing more amount of traffic, then we need to actually switch to a hardware platform. So BMV2 is pretty slow, like Chong was already mentioning. It can process like thousands of packets per second, which takes us to something like megabits per second type of processing. But whereas Tofino and other hardware platforms can easily go beyond 100 Gbps and like 2 into few terabits per second. So there are also switches that actually take us to around 50 terabits per second. So for that, This is a code snippet that we see below that's written for DMB2, but the same code will not actually work on a hardware switch because this is just a simple kind of like addition and bit shifting is what we are doing here, but the hardware will not actually take this kind of instruction directly. So what we will have to do is we will have to understand the limitations of the hardware, and then we will have to rewrite the program in such a way that the hardware is able to execute. In this particular example, we are actually taking a bunch of header fields, and then we are just bit shifting and then adding. But this kind of arithmetic operation cannot be directly performed. So what do we need to do then? So some of this, so like Chang was mentioning, there are multiple phases. So one of the phases like the parser, and the next one is the control or the match action table, and in the deparser. So some of the operations related to the header can be performed in parser and deparser. For example, the summations that we are talking about and the here are actually kind of like conducive for when we are parsing the packet. So that is one part that we will have to be aware of. So the instructions will have to be kind of like broken down, and then we have to see which hardware resource is going to be useful for this particular operation. So in this particular case, the parser and deparser can actually take this, and then we will have to fit the rest of the logic into the middle part of the match action unit or the control block. Can we move on to the next slide, please? So when we talk about the control portion, there are certain hardware resources that are available, that are actually available with the hardware, such as like a hash engine, there is a crossbar, and there are other hardware resources. But in general, it can actually only take two inputs. What this means is like it has its own line like bus width, and it can process only two inputs at any point in time. So the previous statement that we had has to be broken down in such a way that the hardware pipeline is not processing anything more than two inputs that are worth of the bus width type of a thing. So this actually takes us to like most of this is actually written as part of the compiler. So a compiler can actually kind of like try to synthesize your program, and then it can generate some very detailed messages. This does not map to the particular hardware that we are actually talking about. But there are also other artifacts that are generated along with the compiler output that are very useful. So this is an entire session by itself. For cutting it short, we actually try to port the code from DMB2 to Tofino, but this is not like the traditional like or the legacy type of porting that we do from like say Intel processor to AMD processor type of thing, where we change the compiler flags, but we have to kind of like sometimes rewrite the entire logic, break it down, and then fit it into parser. It's like a non-trivial pipeline or non-trivial procedure that we will have to follow. And in certain cases, it is also a little bit of trial and error, where the resource mapping that we actually envision that the compiler will support and then it will fit the hardware may not support it, and we will have to actually reiterate the process in order to fit the hardware. So this is not like a kind of like compiler will take care of everything for me type of a situation, which is usual in the GCC type of like high-level programming languages type of a situation. Can we move on to the next slide, please? Yeah. So quickly shifting gears, this is another topic that is actually that is very important when we actually go into the high performance experiments. So like BMV2 and Tofino on two ends, where BMV2 is able to actually process like a few megabits of packets, and Tofino is able to process like 100 Gbps or like terabits of data traffic. There is also this two extremes where there is KP. I think most of you would know. It's a Python-based library that gives you a breadth of packet manipulation features, where you can generate packets that precisely the ones that you want with the payload set to some kind of like semantics we can have across payloads and something like that. But the main problem with KP is it is actually a pretty low rate traffic generator. While it can be used for functional purposes, it cannot actually scale for some of the high performance testing that we are doing. So in that case, like there are a few traffic generators based on FPGAs, based on specialized hardware. And in this particular case, we actually looked at DPDK-based packet generator for generating close to like 100 Gbps of traffic per interface. So the interface speed itself was 100 Gbps, and DPDK packet generator was able to actually generate more than 90 Gbps and somewhere close to 95 Gbps when we had a dedicated NIC. I think we will see that a little later. But this is actually having a lot of like, it can replay packets at a very fast rate, like close to 100 Gbps, but at the same time, the features are a bit limited. So what we have to, in some way, we will have to do is we will have to maybe have Scapy generate the deeply manipulated packets or deeply crafted packets, and then we will have to use them, use the PCAPs within the DPDK package in order to generate it at a high rate. So it's also like a pipeline type of a thing. Scapy generates something and then it feeds it into package gen, but this is offline. So it's not like Scapy generates it and then it's all not online, where Scapy generates and then sends it to package gen, and package gen multiplies it the rate or something like that. So offline, we have to generate the packets, crafted packets, and then we can use it with the DPDK package gen. Or we can also have a few options of generating random packets with the DPDK package gen. So we will actually use some of this in the later part of the talk. But this is at a high level, we were actually using some of these traffic generators. Can we move on to the next slide, please? Okay, so I'll hand over to Ivan to take over. Thank you.
Hello, everyone. Thank you very much, Ganesh. Yeah, so I will be going over the demo, but before that, I wanted to take some time to go over the nodes as a useful traffic generation mechanism on the Fabric testbed. And shortly after that, we'll also go over some common pitfalls and limitations that we have experienced for this experiment. So it's very important to consider that when reserving certain resources or certain virtual machines on host nodes on the Fabric testbed, that we need to isolate specific host worker nodes on the specific site that we're looking to reserve virtual machines on. So if you see on the right-hand side, we have a summation of all the resources that are allocated or stored on a specific site. But right below that, we have three distinct host nodes on that site that we can use to isolate virtual machines when experimenting on high throughput experiments. And then once we're able to isolate virtual machines on different host worker nodes, we need to ensure that we reserve dedicated high-speed NIC interface chips to ensure that 100 Gbps are being transmitted to the ports on the Tofino switch. From there, the roles of the nodes are very important and very useful, where they become packet generators and packet replay engines, similar to what Ganesh mentioned in the previous slide, where Scapy is very useful for packet manipulation and packet creation. as well as pktgen being useful for replaying pcat files generated from Scapy scripts. And with that, we're able to the end result is going to be reproducible high throughput experiments that we see in our n by n topology on our experiment. All right. And then going from there, we're going to be going over common pitfalls and limitations. So when configuring the switch daemon, it's very important to know to terminate any existing daemon instances from previous experiments. This is a very, very easy issue to kind of fall under, but when you know what to look out for, it's very easy to kill a switch daemon instance when you know when to look out for it. So just when running new daemon instances, make sure to terminate the existing ones if there are existing ones. The second one is the pitfall is if a kernel driver is not loaded properly. When downloading the Mellanox package, we need to ensure that the kernel is reloaded and the operating system is restarted to ensure that the high-speed data transfer or data forwarding is configured correctly. And another thing is when hosting on different sites, we need to ensure that the virtual machines hosted on specific sites are located on the terabit core link. So going back to previous slides, just for a better demonstration, right here on the front page of the Fabric Testbed website, on this yellow line here, these are going to be all the sites that are located on the terabit core link, and this would allow for high throughput experiments to occur. In the worst case scenario, maybe the shortest path to, let's say, Atlanta or Florida here is going to be the 100 Gbps links. If we're going to have multiple virtual machines sending traffic between this link, it's going to hinder the throughput very much in that case. And then fourth limitation here, we momentarily spoke about this, but we need to ensure that virtual machines are placed on different hosts, not on the same host. And this just produces the fact that there might be shared resource contention. And then finally, there is currently an infrastructure limitation. So with setting up a topology, it's very easy to set up an n-by-n mapping. But at this current moment, if we're passing through one specific switch, there's only 8 active ports active at the moment on any switch on any respective site. So the current switch computational throughput is just 25% of what it potentially could be. All right, and then with that, let me start the demo. So I'll stop screen sharing and screen share the demo screen. All right. Okay, here we are. Just to give you a good example, I wanted to kind of present the topology that we'll be looking at. So we're doing a 4x4 topology where we have 4 receiver nodes and 4 sender nodes occurring in one moment. So we have 3 sites on the Washington location, or 3 virtual machines on the Washington site. And we have 3 virtual machines on the Salt location and 2 more on the New York location to add up to 8 nodes in total. Now, when experimenting with the Fabric testbed, it's very important to first import the Fabric library, and I have a link here whenever we publish this artifact if you want to refer to any of the documentation. And from there, we can start experimenting with creating a slice and reserving any resources that we need. So for example here, I created a slice with the name of my experiment. I made sure to host the P4 on the star site where it's located. I added that switch to the slice so that once submitted, we have the proper resource. And this step right here is going to need a manual kind of verification and updates. Once again, we need to find the sites that have isolated worker nodes and reserve virtual machines on those nodes. So in this current topology, like I said, we have the Salt location, New York location, the Washington location, with the values being the number of available worker nodes that they have. From there, we can set up variables with the resources that we need, including disk storage, the type of operating system that we're looking to use, as well as the model of the NIC interface chip that we're going to be using. From there, we can create a subnet where we'll be adding layer 2 networks for communication, and we can start adding the nodes and their components onto the slice, as you can see here, where we have a for loop, where we have a current node with the name of node counter as we're iterating through all the sites with the site details, the number of cores, RAM, disk, etc. And then from here, we make sure to have the node network interface chip mapped to the P4 port, as you can see here. And then from there, we can freely submit the slice. And once this is all done, you'll see a verification step, as you can see here, where it has a summary of all the details that the slice has, including nodes, the subnet and its networks, as well as the interfaces. All right, and once we have that, we can actually start compiling and running, compiling and executing the P4 code. So we'll need to acquire the switch from the slice and upload whatever files we're looking to upload onto the P4, where we can then start the Tofino development environment and compile whatever logic we're looking to compile onto the Tofino switch. From there, once we have that, we can actually execute the P4 program and start the switch daemon and configure any of the switch ports that we're looking to have active and listening to any traffic sent by nodes. So that can be done as such, where we have commands PM port add, PM port enable, and PM port show to start up and have specific ports listening to any traffic being sent their way, and we can use PM show for verification to make sure that ports are listening and they're issuing traffic correctly. As you can see here in this example, we have specific ports being active 1 through 2. We also have their speed, which is 100 Gbps, and then frames received and frames transmitted. Yeah, once we're good with that, this here is actually a script that sends specific commands to begin the switch daemon. But in my experience, I would say it's usually better to do it manually, just so you can verify that everything is working properly, which I already have a terminal up and running right here. So once we're running the actual experiment, I can show you how that would look like. All right. Okay. Give me 1 second. Let me just restart my browser here. Looks like it was frozen. And then from there, once we have all the ports listening and enabled, we need to populate the switch forwarding table to map the n-by-n pairs. In our case, we have a Python script that maps ports 1 through 4 to ports 5 through 8. And it's a very simple mapping just to kind of forward packets from node 0 to node 4, for example. All right, and from there we have the P4 switch configured and ready to go. And now we need to have all the nodes having their respective dependencies and packages installed in order to begin sending high-speed data packets. So things that we'll need to download is Gbps for packet generation, the Mellanox driver in order to bypass the kernel for high throughput or high-speed transfer, and then DPDK and PKTGen for to utilize the application to start begin forwarding packets. As I said, when downloading the Mellanox driver, it's very important to reboot the system. This will, of course, will take up to 20 seconds, so you just hang tight while you're waiting there. And then once you SSH back into the virtual machine, the Mellanox driver should be already set, all set and ready to go. Now, one last thing for setting up this the node's dependencies, we need to allocate huge pages. In order for fast retrieval, we need to have the pages on the virtual machine to be 2 megabytes or higher for fast retrieval. So this command will do something like that for you. Okay. And then from there, this is just a quick way to retrieve PCIe address details to configure the PKTGen application to use the network interface chips address to begin forwarding packets. All right, and now with all that, we can begin using PKTGen to actually test the topology. But before that, just as a quick verification step, I have two terminals up here with PKTGen active to show that the switch is configured correctly and sending packets correctly to its destination. All right. All right, so as you can see here, I used a command start 0 to begin sending packets to its destination, which its destination is 192.168.05. This here is the IP address of node 4 in our topology, which I believe was on the wash location. And it's sending packets via the switch, which if we use PM show, port manager show, we will notice that port 1 receiving packets from node 0 is increasing in the packets received from node 0, and subsequently also transmitting it to node 4 via the switch. As you can see here, the difference in value. Just to make it a little easier, we can use PM rates show to show the total capacity of the port being used. In this case, it's close to 100% or all of the port's capacity being used. If we go on the opposing node, we can see that packets are actually being received from node 0 via the switch. So this is just a very good way to verify that at least one of the configurations are set up correctly. All right. And then from there, with the notebook, I will begin this just because it takes a moment. We can now expand that to every node, where we'll need to configure the IP source and destination, as well as the MAC source and destination, to make sure that packets are being accepted by the complementary pair, complementary receiving pair. And when we go on the switch here, we'll notice in a moment it's going to start receiving packets. This usually takes around 50 seconds, so just bear with me here. There we go. Yeah, it started receiving packets. And as we can see, all ports are active. And if we look at, if we were to look at every node and start beginning to capture the packets being sent, we would see where it was being sent from and where the intended destination is. All right, and with this just is a good way to check that the topology is configured correctly and packets are being received in the right manner. And with this, we can begin actually performing some experiments, which in our case, we wanted to evaluate the checksum logic that we have hosted on the P4, which to do that, in order to evaluate any collisions or any hindrance on the throughput of the P4 switch, what I needed to do is use Gbps to generate 1 million packets in total and distribute them across all nodes with 65,000 differing payloads in order to check if there's any collisions occurring on the P4 switch. Yep. And what we'll do is we'll use the host node SSH details in order to send these scripts over to those nodes and execute them to have PCAP files to be able to use during the PKTGen replay step of this part, which is very similar to what we did when we were testing the configuration or the topology configuration. Once we have the PCAP files generated with Gbps, we can use the MAC addresses and IP addresses, as well as using this command enable 0 PCAP to listen to the PCAP file used as a parameter when starting up the PKTGen application, as you can see right here, to replay the PCAP files generated. And with that, we should be able to see, we should be able to capture packets on receiving nodes and send packets at a headline rate on sender nodes. And with that, that's the end of my demo, and I'll send it back to Casey Wang.
All right, that's wonderful. So now we will move on to the Q&A. Let's begin with some questions that have been submitted during the presentation. So for now, yeah, we can have our speakers turn on their video and then start with the first question. Question one, a question about multicasting in the Tofino switch. How are the multicast copies queued to the respective egress port queues while the packet is held by the packet replication engine PRE, sequentially one port at a time or simultaneously to all the egress ports of the multicast tree? In other words, can a queue of multicast packets form in the RPE because the time it takes to queue all copies of the packet can be longer than the minimum inter-arrival time of multicast packets? If yes, what is the maximum size of the PRE buffer?
Yeah, I'll maybe take this question. So this is actually a pretty good question, and it's also a little involved. The multicast thing for multicast, we need to actually pre-configure certain things that we did not cover here. But the thing is, like the configuration will have to actually set something like a multicast. It has to set up a multicast group so that when we are actually sending the packet out of the ingress deparser, it knows that it is a multicast packet and it has to actually go to multiple of the egress ports. So having said that, in between, there is actually a switch fabric and there is also a little bit of like the multicast tree is not actually like a multi-level tree in this particular case, but it is more like there is a crossbar and it actually kind of like there is a shared buffer and it has to actually replicate that packet in the corresponding egress port buffer. So that is what it takes architecturally. Different hardware actually realizes it differently in that way. Whereas like some of the hardware has crossbar switch fabric with storage with a little bit of buffers built into the crossbar itself. And Tofino actually kind of like has its own way of actually doing it. So overall, this is a shared packet architecture. It's not like it is multiple point-to-point type of thing. So it is truly multicast in that sense. But always with multicast, since we are using up multiple ports, then the corresponding contention will have to be taken care of. So
Thank you.
that's the only thing. Yeah.
The next question, how can I debug throughput or performance issues across Fabric sites?
I think we should answer that one. So you could actually use one of the topics I kind of described during my demo, where you could use the command line interface of the switch daemon to check and use port manager to check which ports are active or not. As I kind of showcased, you can use rate show to see how much of the ports are actually, how much of the capacity of the ports are being used. And if packets are being transmitted correctly, then that's just a good way to see if the switch is working as intended.
Thank you. The next question, which traffic generator should I use for my experiment?
So that is a slightly detailed topic in itself. So if we are targeting a functionality, for example, like some people target like I want to implement IDS functionality, IPS functionality, something like that. For functionality, Scapy is the best in terms of like generating package that we need. And then trying out different like cross packet semantics type of thing. First packet and 100 packets should look same. These type of semantics for this Scapy is very good. But when we actually have to move forward with the rates, Scapy is not as good in terms of scaling. So we may have to kind of like look for like hardware-based, like FPGA-based traffic generators are there, which we use to generate like 10 Gbps line rate traffic, and then DPDK-based ones that generate like 100 Gbps. And then there are some dedicated NIC-based, like for example, ConnectX NICs can be used for generating like up to like 200 to 400 Gbps traffic. And in one of the cases, Starlight, their team, they demonstrated with the dedicated hardware, they were able to send and receive 400 Gbps with a pretty expensive hardware. So there are a wide variety of options, and it's up to the availability and what kind of thing that we want to do.
Thank you. The next question, how do I reserve resources if they are already in use by other users?
I can take this one. Usually on Fabric, the resources are reserved by slices. So if you are interested, for example, the only P4 switch on star side, you should be able to go to that site and like list the slice that is actually using that hardware. If you can not find out how to do that, you can contact Fabric team for details. And once you find out the slice name for that specific hardware, you should be able to find the end time for that specific slice. And then you will be able to make an advanced reservation ahead of time to reserve the piece of hardware after that end time. So you can wait until your slice starts. So then you can start using the hardware that you want to use by making this advanced reservation.
That's great. Then what are the performance differences between BMV2 and Tofino?
I can take this one. A BMV2 is more like a software switch. So it takes the packet and then it is trying to do everything within the CPU pipeline. So it is not as fast. So it depends on the CPU resources that we actually dedicate to the particular switch. So having said that, what we were seeing is the BMV2 based implementation was scaling to like 10 Mbps or even a little bit more, up to like less than 1 Gbps is what is the maximum that we were seeing. But whereas when it comes to Tofino, it can actually support close to terabits, and it can saturate the entire terabit core at some point.
All right. What makes programmable P4 switches on Fabric particularly valuable compared to traditional networking approaches or software-based solutions?
Yeah, I'll take that. These are actually like the P4 switches on Fabric is particularly valuable because like as always network engineer we want not as network researchers, we want to actually showcase our work and show that okay, this works on a production class switch. But it is not very often that we have that kind of a resource to actually experiment it. So uh, while we actually say that theoretically it will scale, kind of a thing, and then we usually publish or like we conduct experiments at very low scale, like 10 Gbps or 1 Gbps type of performance experiments. So the P4 switches on Fabric is particularly very valuable when we want to conduct experiments at like close to terabits and then show that, okay, this can really scale and this is of production quality type of thing.
Okay. Now, next, if we wanted to process the payload instead of just the headers, I think the Tofino are unable of doing that. So what would you suggest?
That's a good question. There are limitations with every hardware platform. Tofino can process say up to 200 to 250 bytes within the payload. But there are actually like NVIDIA switches can actually do slightly better, and they can go up to like 500 bytes within the payload. Mellanox switches or Spectrum switches, as we know it today. There are also like smart NIC DPUs that are coming out that can actually really do deep processing within the payload. So there are different hardware platforms that are available. And if we select the right platform, we should be able to do the payload processing that we desire. For example, we recently have some SmartNIC DPUs, NVIDIA DPUs in Fabric that we can use for complete payload processing, whether it be a jumbo packet. So
Okay,
what we're talking about is like 8,000 bytes type of thing.
that's great. So where do you see this kind of high throughput setup being used in practice?
In practice, actually, there is a very big gap between the research and the practice when it comes to like, for example, in practice, if we want to even deploy SDN or something that is deeply programmable, we don't have that kind of like environment to test it out in the first place. So that is exactly where actually Fabric is doing a very nice job of trying to create a high speed and high throughput distributed environment where we can actually conduct some of the high throughput experiments like we discussed today. So that is going to be very useful in that sense, trying to bridge the practice and the world of practice and the world of like research world. So that's where I see this going.
Yeah. So you touch on some limitations. What is one challenge that is most especially tricky to work with?
Ivan, would you want to take this? Or like...
So for the most part, with our very first iterations, we did have some trouble with reserving specific host nodes. So for example, the Fabric allocator, whenever you reserve a node and you don't specify which worker node you're going to reserve it on, it could reserve it on isolated host worker nodes, or it could reserve like the virtual machine on the same node. So if you're using, let's say, like a basic NIC where they share the same hardware piece, and in a case like that, it's going to very much hinder the high-speed data transfer that you're going to be experiencing. So that was one bottleneck that did give me a little bit of trouble.
Thank you. The last question. If someone wanted to try this themselves on Fabric, what's the first thing they should know or be careful about?
If they want to try it on Fabric, that is actually like Fabric is also a little bit of reproducible, like it's built with reproducibility in mind. So once we actually have this artifact published, then anybody should be able to take it and then they should be able to reproduce the experiment. Having said that, what they should be careful about, definitely the resource allocation part and reservation part. They may need to plan it ahead. But for that, I don't see any high-level challenges. But there are some kind of like unexpected things that we were actually facing. Like, for example, we were expecting the traffic to flow in a particular path, but it was actually flowing in a different path. So we had to actually go down and then we had to do a little bit of explicit routing, which is also available in Fabric and to achieve some of this. So I don't expect any issues, but in case if there are issues, please feel free to get back to us.
Sure. Well, many thanks again to our presenters, Kong Wang, Ganesh Chanmalai Sankaran, and Ivan Torres today. In addition to our presenters, we would like to also acknowledge the behind-the-scenes team here who worked diligently to bring the webinar to production. As we can see, myself and Chelsea Davis, our project manager, has been helping to plan for this webinar. So next slide. Thank you to the audience for your participation into the webinar today. In addition to the recording, we'll also email everyone who has registered with a list of resources. The slide deck will be shared, and you can see there's a Connect with Us forum. I hope you will connect with Fabric team for more questions or support. Next slide. The next webinar will be Mastering Fabric Tips and Tricks webinar series. It will be on May 19 at 3 p.m. Eastern Time. The webinar will be focused on existing users, AI researchers, and testbed administrators. We would appreciate it if you know someone who might be interested about this and to share it with your community. As a final reminder, if you're a Fabric user, please submit your Fabric matrix and make sure your project description in the portal is up to date. We do use that information for outreach, and we do promote it on our website. So thank you again, and have a wonderful day, everyone.